Good afternoon. My name is Ashley Beard, and my education includes a bachelor's degree in astronomy and astrophysics from Florida Tech, and I'm currently working as a research scientist at Spectrum Bullpen in Florida's Space Coast. Today, I'm going to talk to you about our applications of GNU Radio as a radio channel identifier using machine learning. To introduce this project, I'll share our conclusive claim of the results we've achieved. Using GNU Radio scripts, we modeled a neural network that differentiates between open and occupied radio frequency channels. We confirmed that this neural network is more accurate but less efficient than a classical power estimation algorithm, and is less accurate but more efficient than its neural network predecessors. This presentation will dive a little deeper into the motivation, the process, and the analysis of this endeavor. I want to first go over a little bit about Spectrum Bullpen and what we do and what to stay tuned for. Next, I'll share the motivation behind this project as well as some background history on neural networks and cognitive radio to give a better understanding of the reasoning behind this project. Then we'll get into the experimental setup and how we use GNU Radio to both generate large batches of training data and to design the algorithms we've tested and compared. We'll go through the analyses we conducted on the algorithm results and what these results ultimately mean for the field of signal processing and cognitive radio. Lastly, I'll leave you with a short preview of Spectrum Bullpen's current projects, one of which also relies heavily on GNU Radio and its Python interpreter. Let's get started. Spectrum Bullpen is a small contracting business based out of Palm Bay, Florida. It was founded in 2016 by Raymond Shaw, who worked in spectrum management and electronic warfare at Lockheed Martin and Northrop Grumman after serving as a strategic spectrum planner at the end of his 22+ years of service in the United States Marine Corps. We're celebrating 5 years contributing to the leading edge of spectrum management and electronic warfare, and we've had past contracts with the DoD, the Navy, and we recently have been awarded the first phase of an Army SBIR. Our focus areas include RF spectrum planning and execution, software radio solutions, machine learning applications, and dynamic spectrum access, or DSA, policy generation. Our motivations behind designing a channel identifier using machine learning came from some of the previous work we came across in our preliminary literature review. There is a wide variety of neural networks applied to different types of RF classification schemes, including modulation classification, symbol rate prediction, as well as RF signal identification. Not only that, but there have also been machine learning work done in GNU Radio in the past. To name one paper by Tim O'Shea and Nathan West, their radio machine learning dataset generation with GNU Radio. Part of our motivations is to make a first contribution as a company to the GNU Radio community. Sharing a project like this is meant to show channel detection as a further application in more unique topics such as spectrum sensing, cognitive radio, interference minimization, and DSA policy generation, like I mentioned before. The DSA applications are something I'll touch on briefly at the end of this presentation when I discuss the future work. This table here goes over some previous literature relevant to this work. The earliest paper in this list is from 2007 by O'Shea, Clancy, and Ebiad. They similarly use GNU Radio to design a signal classification algorithm. However, they do not use a machine learning in this iteration. They use multi-threading and a connection to a power processing element, or a PPE. The next related work I want to mention is a machine learning approach by O'Shea and West. This one is called Radio Machine Learning dataset generation with GNU Radio. Our work is somewhat based off of this same concept of using simulated radio signal data to test a neural network model. O'Shea and West use a convolutional neural network, or a CNN, whereas we use a feed-forward neural network. We also use the simulated data with a traditional power estimation algorithm to compare the performance of the two. In 2020, Rodriguez and Desati also utilized GNU Radio by designing an out-of-tree module to use machine learning, and they use this to classify types of signal modulations. The next one is a paper by Tumularu, Wang, and Yado from 2010. They want to solve the same problem we propose our work under, to use spectrum sensing for more efficient utilization of the radio broadcast spectrum. They use a machine learning model called multi-layer perceptron, or MLP, which is a somewhat different approach than our own feed-forward neural network model. The results of their paper show that the best performance of their model is 95.2%, which is a nice, very high percentage accuracy. Presented in the 33rd Conference on Neural Information Processing Systems, Cao and Gu described their neural network model using stochastic gradient descent and a sigmoid activation function. These two algorithms are what we used in our neural network model. However, the data they used is different from ours in the sense that it's a normal distribution of parameter values, whereas our data comprises of a randomized sample distribution, which I'll go over a little bit more later. The next related work is a novel approach worth mentioning, where the authors Han et al. Use GANs, or generative adversarial networks, to generate and predict signal propagation maps in order to identify a radio channel. The work these authors did contributed greatly to the cognitive radio field and machine learning applications thereof. Finally, I'd like to mention Solanki et al., their work from 2021, and their model called DL-SenseNet. They contributed a deep neural network consisting of both short-term memory layers and CNN layers to recognize both temporal and spatial dependencies of data in their digital signal data. Now that we've gone through an introduction to the modern work done in the field of spectrum sensing and cognitive radio, I can describe in more detail how our project was designed. The intention of this paper was to design two algorithms, a simple neural network and a non-machine learning algorithm, to compare the performance of the two, with the goal being to create a neural network that can distinguish used from vacant radio channels with a higher performance. This performance would be either in terms of higher accuracy, better efficiency, or both. The end result of this process has provided a lightweight, mobile, and low-cost channel identifier with the help of GNU Radio. I'll go into more detail on the two algorithms later, but to give an idea of what they entail, the non-machine learning algorithm is a power estimation algorithm, is created using GNU Radio. It was made to provide a baseline in analyzing the performance of the neural network. The neural network is also implemented in GNU Radio. It was created as a simple feed-forward neural network, meaning data travels directly from one layer to the next without having all the neurons in each layer fully connected. Both of these algorithms are fed simulated signal data to produce results that tell whether the frequency being observed is occupied or open. And this data is simulated using a GNU Radio flow graph. The frequencies shown in Table 1 are common 2.5 gigahertz band Wi-Fi frequencies used in the US. This is according to the IEEE. For each data set, we randomly chose 5 frequencies to use for the occupied channels, and the other 5 frequencies were to be used for the open channels, where there was no signal. As a side note, I've included what software and packages we used so that anyone who chooses to recreate this work can have the same system set up. For this project, we used a Windows 10 system, a GNU Radio version 3.8.00. The Python version associated with the GNU Radio version is 2.7.10, and extra Python packages we used for this were, for the 2 channel identifier models, included the time package, the random, PMT, and NumPy packages. And Spider was the Python compiler that we used to modify our GNU Radio scripts. It came in very handy for viewing matrix and variable sizes. Here, I show the GNU Radio flow graph we used for our data creation. You can see that there are 5 cosine signal sources with the same relative amplitude value of 0.05 and a Gaussian noise source of relative amplitude 0.01. The 5 signal sources have randomized frequencies chosen from the table on the last slide that I mentioned. The sample rate was set to 166 megasamples a second, and this is based off the Nyquist-Shannon theorem. The SNR for this data is 44 decibel milliwatts. The raw IQ data is throttled and then sent to a file sync and saved in a local directory. GNU Radio has a tool that allows the user to generate the flow graphs into Python files, which allowed us to loop this flow graph and run iterations of it to generate our 800 dataset files. These files were split up into 640 teaching files and 160 validation files. That's an 80% 20% split. These teaching files include labels to pair with the data so that the neural network learns what to categorize for each data set. The validation files are used to test the accuracy of the neural network after it's been trained. The first algorithm I'll go over is the traditional power estimation algorithm. I say traditional because this algorithm doesn't use any machine learning. Shown here is a flow graph used for the power estimation. The simulated signals are set up the same as the data generation I showed before. What is different for this flow graph is the fast Fourier transform block, splitting the added signal sources into frequency bins. These bin values are converted to magnitude squared values and saved as Python variables using these probe signal and function probe blocks on the right and on the bottom. This process is similar to the one used by O'Shea et al. In 2007 from their paper that used the data generation from GNU Radio. This flow graph was also generated into Python in order to have it loop through its functions the same number of times as our data generation script. We chose to compare the power estimation script to a simple feed-forward neural network after conducting a literary review in machine learning applications in digital signal processing. We've seen multi-layer perceptrons used, which are a type of fully connected feed-forward neural network. We've also seen CNNs, recursive or RNNs, LSTMs, and combinations thereof used. These neural networks have been shown to perform to high accuracies of 90% or higher, when applied to things like modulation classification, channel estimation, and predicting signal propagation loss. A feed-forward neural network was the appropriate choice to use with GNU Radio for us and our channel identifier because we only have a simple binary vector stream as our data input. The neural network contains 5 layers. There's 1 input, 3 hidden inner layers, and 1 output layer. The idea is to feed in vectors of data alongside a vector of labels that assign this data classifications. These classifications say either a channel is occupied with a signal or it is open. A sigmoid activation function was used to calculate weights associated with each input. An example of this function can be seen on this bottom image. And you can see the sigmoid function is 1 over 1 plus exponent raised to the negative z, and z is our data set in this case. The data that has the most relevant features associated with the classification label gets the highest weight from the network, and the least relevant data gets the lowest weight. The network uses a stochastic gradient descent algorithm for forward path classifications and uses a backpropagation to recalculate those weights and feed them back into the first layer to start the next training step. We use 640 data files with randomized selections of frequencies to train the neural network, so it will estimate the channel classification on its own when we give it new data that it's never seen before. That's where those validation files come in. After these models were ran and they output their estimated responses, we conducted some analyses on their performance to compare the two. Our analysis section includes an analysis of percent error in our signal detection models, of the random bias in our data generation, and of the compared computational complexity of our models. Let's first go over what the percent error was for each algorithm. The neural network achieved an accuracy of 66.17%, and the power estimation algorithm achieved an accuracy of 49.12%. This shows that the neural network is more accurate as a channel identifier. One reason, though, that the accuracies weren't higher could be because of the way we pre-processed our data before sending it through the neural network. The raw data generated through GNU Radio is IQ data, which are complex values. To process this data to be compatible with the network, we converted the complex values to magnitudes, which caused some data features to be lost in the process. A study from Rahman et al. Has shown lower frequencies are learned more quickly than higher frequencies. So our choice of working with the 2.5 gigahertz Wi-Fi band instead of something like a low frequency 300 kilohertz radio frequency might mean that we need a lot more data to get a higher accuracy. Although the accuracies are not as high as some of the previous work done in this field, we believe our models can be improved in the future to achieve and perhaps surpass the 90 to 95%. The second analysis we conducted was on the generation of the data, not the Python models. This is the randomness testing. Having a true random distribution is important for unbiased data. If the Python functions we use to randomize the data sample selection, were not completely random, but a pseudo-random, then this could lead to a bias in the sample distribution, and which could then lead to the neural network training incorrectly. It wouldn't equally learn every type of frequency signal. The plot to the right shows a nearly uniform distribution of random frequency samples, which is what we want to see for truly random functions. The gap in the plot is only for a frequency that the table had left out, the one that we reference. The third analysis we conducted on the models were the computational complexity. This tells us how much energy the system is expending to run these scripts. The standard notation used to describe this value is using big O notation. This describes the upper limiting factor when an algorithm approaches its bounds. When this value is low, it means the algorithm is efficient and it costs less energy than an algorithm with a larger big O value. All the complexities for the Python functions and the mathematical operations we used in our GNU Radio scripts have previously been calculated by other mathematicians and computer scientists, so we can reference those and combine the functions to get an estimate for the complexities of both our neural network and our power estimator. These results show that the neural network is more computationally intense than the power estimator. However, it is worth noting that since our network is only 5 layers, whereas some previous work uses deep networks with something on the order of 15 layers or more, there is still an advantage to using our model in this scenario. So, I've discussed how we use GNU Radio to simulate and collect digital signal data, as well as to create a feed-forward neural network and a traditional power estimation script. These two scripts were used to estimate whether a set of frequencies had a signal or was unoccupied, and these results were compared to find the more beneficial of the two scripts. The results showed that the neural network had a higher accuracy, but a more computationally intense. And we argue this script is better of the two, with room for future improvements. Some future work that the script would benefit from includes rearrangement of the data pre-processing to allow for complex input instead of converting to magnitudes like we did, and losing some data features that way. The next includes spending some time to use trial and error to optimize the hyperparameters in the neural network. One specific hyperparameter includes the learning rate, which decides how fast the neural network can converge or diverge from the optimum solution. The third way could be to include more layers. This could make the network more accurate, but it would also increase the computational cost of the algorithm. The last thing I'd like to leave you with before concluding this talk is to describe the current research and development we're working on at Spectrum Bullpen, and that you may be hearing more about in the future. Our RF propagation modeling will be using machine learning to create radio signal coverage plots based on many environmental parameters. And another project is using machine learning as well to fingerprint radio transmitters. Thank you very much for your time, and I would like to mention that our code and our data is openly available at this GitHub link, and feel free to take a look at those as well as our company website to see more from us. Thank you very much.